Okay, let's start. Good morning. So we have a couple of things to discuss regarding integral calculus. And then we'll be on our way discussing differential forms, the third topic of this course, major topic. And then we're going to discuss fundamental theorems of calculus in this multivariable setting within the context, within the formalism of differential forms, things like divergence theorem, Gauss theorem, whatever. They're all going to be one theorem, ultimately, once we figure out how to use differential forms. Two things that we need to discuss in terms of results is, well, Fubini theorem. We would like to be able to take a multivariable integral and sort of rewrite it in terms of multiple single variable integrals. That is the Fubini theorem. And the other one is the so-called change of variables formula. I think I'm going to state them, but I'm not going to prove them. I think that's what we're going to do because I'd rather spend more time on differential forms. And they do get somewhat technical. Although they are within our reach. We have certainly done more complicated things in this class, but time is limited. And I feel OK just black boxing them. What I would like to do today is to give an example. Discuss how to compute, Jordan contents of a certain set. Okay? And I hope this is going to sort of exemplify how it's really of a different flavor compared to everything else we've been doing so far. So I want to start with this example. And I'm going to compute its volume or Jordan measure, whatever, Jordan content, in multiple ways. Ultimately, you should say again, well, this S, it looks like it's a nice set. For nice sets, all of these things should give you the same number. Okay. Before I start, are there any questions? By the way, I'm taking attendance today, so there's a attendance sheet going around. So the example that I'm interested in is this. Remember, we defined everything in the context of inner product spaces. So I'm going to take V to be R2. And as before, as usual, whenever I write R2 or a space of tuples, I mean that is endowed with the standard inner product, which is just a dot product. I can talk about orthogonality in V in the standard sense. And my S is going to be, well, it's going to be this diamond. OK? 1, 1, minus 1, minus 1. Well, there are multiple ways of writing this, but perhaps the fastest way of writing it, and when I say S, everything inside is included also. It's not just the boundary. Perhaps the fastest way of describing this, maybe I should ask you, how can I describe the set S? How can I write it, let's say, in set builder notation? There are multiple, yeah. Go ahead.
The L1 distance norm would work.
Yeah, that's one thing you can say. You can say, well, this is nothing but the unit ball centered at the origin relative to this norm, which is this L1 norm. That's probably the fastest way of writing it. So let's write it here. So xy in R2 such that, well, xy in L1 norm is less than or equal to 1. Okay. Now, just because I'm defining a set using a certain norm doesn't mean that for my purposes I'm going to be using this norm. Even though here I'm using this L1 norm, the underlying structure is going to be the L2 norm, or Euclidean inner product, whatever. So I'm not going to be using this L1 norm to compute volumes and stuff. But certainly I can use it to define a certain set. OK. Method 1, I'm going to give you 3 methods. The third method is going to be this Jordan content business, and maybe we're not going to be able to compute it explicitly all the way, but I hope to give you some sense. Method one is this. Well, I can realize that this guy really is, I can think of it as a box aligned with respect to some basis. Okay? So let me define this. So what are we trying to do? Compute, let's say, this. I'm going to remind you what these are in a second, etc. I would like to compute things that are similar to volumes, or areas in this case, because two-dimensional volumes are nothing but area. OK. Method one is to realize that this set is really an aligned box relative to some basis. And so if I were to define, for instance, beta 1 to be 1, 1, and beta 2 to be 1 minus 1, that's a basis, right? And in fact, when you think about it, if you were to take the dot products of these, that gives you 0. So while beta, consisting of beta 1 and beta 2, is not an orthonormal basis, these don't have norm 1, it's an orthogonal basis. So they're orthogonal. They are not normalized, right? So the norm of this is 1 squared plus 1 squared is 2. You take the square root, the norm of this is square root 2, right? And likewise for this, these are not normalized vectors, but they're orthogonal. OK? And so what do I need to do then? Well, I need to figure out based on our formula, and S is a beta-aligned box. So now I want to use this linear algebraic definition that I had updated last week. What does it say? Or maybe we can do it in 4 different ways, actually. Using the literal definition, I have this, OK? So I need to use this m sub beta. Goes from E into R2. And how does this operate? Takes beta 1 into, let's call it sigma 1. This is 1, 0. Beta 2 into sigma 2, which is 0, 1. Right? Now, under this transformation, what happens to this box? What happens to this S? Well, I can just, again, as before, keep track of the corners. So for instance, 1, 0. So we need to compute the inverse of this. Not sure if I want to go down this route. I feel like it's going to get complicated to compute. Let me think. Let me do it like this. You can do it like this as well, but in this case, there is no need. I think it makes it a lot more complicated. Relative to this orthogonal basis, S is an aligned box, meaning in one direction I have this beta 1. In this direction I have beta 2. Well, in this case, the definition really tells you, ultimately, that the volume of this should be the length of this times the length of this. Okay? And so now we need to look at those. Of course, these lengths are nothing but, so this is 1, using the Pythagorean theorem, whatever. This length is root 2, and so is this length. Oh. So that's the area method 1 gives. Okay. If we were to use this m sub beta business, again, we would need to incorporate the norms of these vectors, and that would give you the same thing, ultimately. Any questions about this? Yeah.
These guys, right here, right.
Thank you. Yes. Yeah, in fact, this m sub beta is going to be rotation by 45 degrees. Because ultimately, I'm going to end up with a standard box, I know. So this is going to be rotation by 45 degrees, and then a shrinkage by root 2. So, OK, I'm not going to write it. You can write the matrix and stuff. Let's not get into the linear algebra. So this is the first way of doing this. Second way of doing this. Well, I'm going to define this B to be this box aligned with respect to the standard basis. Right? At the standard box. Its volume is, again, the product of the lengths. 2 times 2 is 4. And I think at this stage, it's OK to say, well, S should be exactly half of B in area, right? Because you're just chopping these two. We can sort of try to make this more formal, but I don't think we need to try to make it more formal in this case. But at the very least, this volume business should match with your intuition. Certainly, that should be true for very nice things. So this is, I guess, the pattern that is emerging. Remember, in Taylor approximation business, I told you that algebraic cases should work based on your intuition, polynomials. You should be able to expand things and so on, and it should match what Taylor gives you. And here, too, even though we're sort of building this more abstract theory, when you apply that theory to more concrete, more natural example, more, how to say, I guess I can still call this an algebraic example. Algebraic cases, again, it should give you what you expect. OK. Now, really, the main problem is these Jordan content businesses. OK, I just wrote these two methods to give you an idea as to what we should be expecting. So 2 seems to be the candidate number for the Jordan measure of this. OK. So now let's try to compute really this and this. So method 3. Of course, in this case, going through the definitions is kind of overkill because you can compute it using much simpler methods. But I think it's still a good idea to unpack these definitions and see how things work. So let's, for instance, start with this. Okay, let's remember what this means. This is the upper or outer Jordan content of dimension 2 of S. S is a bounded set, and for any bounded set, this upper Jordan content exists as a number. So this is going to be a number ultimately. Lower Jordan content is going to be, again, a number that is well defined for bounded sets. Now, what is the definition of this? When you see this outer Jordan content, that should be an upper integral. That's why I put the bar up there. Okay. Now, instead of thinking of S, right, instead of thinking of the sets, I'm going to think of the characteristic function of S. This is a function that is defined on all of R2 that gives you 1 if you feed to it some point in S, 0 otherwise. Meaning, it's a function whose graph, right, it's a graph on top of this, is lifted up by 1 unit over S, and it's 0 otherwise. It's a 0, 0, 1 signal, if you want. Okay? And so this outer Jordan content of S is nothing but the upper integral of its characteristic function. Over what? I gave it as an exercise, but over some box that contains S. In this case, I think it's a nice choice to take B here. Yes?
Can you explain what B is again?
B is this box.
Oh.
So it's this box.
Oh. Yes.
It's a standard box that I'm thinking, so for the purposes of this example, I'm saying I should be able to compute the volume of B nicely. S is sort of like more complicated. I don't know how to compute it, even though I can. I'm just pretending that I cannot compute it. So this is this. And again, let me signify this here. The symbolism or the formalism that we defined requires that you write it like this for now. Okay? D of the tuple. Remember, when we were discussing differential calculus, I differentiated uppercase d from lowercase d, and I told you later on we're going to use lowercase d for differential forms. Now, this d is not the same d as the d in differential forms. It's a different d, although they are related. Okay. Not exterior derivative. Exterior derivative, we're going to define later once we focus on differential forms. And again, what is going to be the difference? Ultimately, the difference is that this integral is an unsigned integral. Okay? It's an unsigned integral. In one dimensions, sometimes it matters if you integrate from here to there or from here to there. And you write like this. This would be a signed integral. I'm not using a signed integral here. It shouldn't matter, for instance, in this case, whether you use the clockwise orientation or counterclockwise orientation to compute the area of this. It should give you the same number. Okay? So for the problem set, due this Friday too, you're going to look at barycenters and averages. These two don't depend on the orientation. Okay? These are not signed integrals. These are unsigned integrals. We're going to switch over to signed integrals once we start talking about differential forms. Okay. Now what is this? Whenever you see something like this, in the case of integrals, you should always think about a minimax or maximin. Okay? So this is supposed to be an upper proxy, or it's a proxy from without. So this should overshoot the actual integral. Okay? In other words, the actual volume. Ultimately, I'm expecting this guy to be something larger than 2. Let me continue writing here. So now I need to open this up. How can this be an upper integral? Well, I'm going to be first taking upper Darboux sums over relative to some partition. Then I'm going to infimize, I'm going to minimize that, right? Because if I'm taking the uppers, that means that I'm taking a max. Whenever you take a max, to get something meaningful, you need to take a min over the maxes. You have to sort of alternate min and max. So when you write this down, first of all, you have an upper integral here, or upper sum of this function relative to some partition. Then you infimize this over the partitions. Partitions coming from or aligned with respect to which basis? Let's say the standard basis, sigma 1, sigma 2. Sigma now is a standard basis. Okay. Now you need to open this up. What is this? This is a finite sum over all pixels coming from this partition. Curly P. Now what do I need? I need the volume of the base times height information. For the height information, by definition, because I'm using upper sums, I'm going to look at chi sub s. This is a function. I'm going to restrict it to this specific partition cell or pixel P. I'm going to look at its sup. So this is my height times the volume of this pixel. Okay. I'm just going through these definitions. I'm unpacking these things because it can. So this is even though ultimately it's not very sophisticated because like it's multiple sort of like things packed together, it might become an issue to really understand what is going on. So that's that. Can I say anything specific about this? Well, this is a very nice function, okay? It is either 0 or 1, no matter what x, y is. Okay? And so what I can say here then is that if this pixel that I chose intersects with S, this is going to be 1. Otherwise, it's going to be 0. Okay? I think at this point it gets a little bit more abstract. Let's try to specify. I'm going to draw some pictures. That's my B. That's my S. Here's, for instance, one pixel, pixelation, partition. Oh, I can just take this. Okay. This is a partition of B that is aligned. Okay, that's B. It's the outer box. And the so-called unknown shape is S. Let's call it P1. Okay? So I have 4 pixels in this specific partition. Okay? So 1, 2, 3, 4. What is the sup of chi sub s on this specific box? 1. Why is that? Because I'm thinking of chi sub s. Chi sub s is a function whose graph is like coming this way, and it's elevated only over this, which means that over this pixel, it is also elevated too. But by definition, if it's elevated, it's going to give me 1. Okay? So for this partition, well, I'm going to have 1, 1, 1, 1 for height information. But I need to scale everything by the sizes of the pixels themselves. What is the size of the pixels? Any one of these pixels? Well, this length is 1. Okay? This length is 1 as well, which means that each pixel has area 1 also. Ultimately then, the upper Darbousam is going to be 4. Okay? So it's overshooting the target, but that's fine. Okay? This is a rather crude partition. It's not really distinguishing this. It's saying OK, so I'm seeing something, I'm going to give it 1. But of course, if I were to look at the lower Darbousam, what is this now? 0, right? Why is that? Because, again, I focus on, let's say, this pixel. Over this pixel, I'm looking at chi sub s. There are certain regions where chi sub s is zeroed out. So the lower is going to not see this pixel. For the lower sum, it's going to say, well, part of the shape is not included there, so I'm just going to not count it. Okay? So that's a lower proxy for the target. Does this make sense? Now let's do one more. Let's use this color. This is what I had started with. Now I want to add more pixels to get a better understanding. When I refine this any further, I would expect the upper sum to decrease and the lower sum to increase. Okay? And so let's do this. Let's go one step further. course, this corner is exactly here. Okay. And so again, I'm going to look at, now this time I have 16 pixels, right? 1, 2, 3, 4, 16 in total. For each of these pixels, for the upper, I'm going to say, oh, does this pixel intersect with S itself? I'm just going to count those that do. For instance, this is going to give me 0. 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 All of the pixels intersect S. So I have in total 12 pixels that intersect the shape. Okay? This is coming from the height information. But I need to scale it using the volumes of the pixels themselves. What is the volumes of, what is the areas? Well, if this is 1, this is 1/2. 1/2 times 1/2 is 1/4. Yes?
For the very outer corner squares, do they not intersect the shape enough, just barely, to be 1 under the max? Like, do they contain that point? Sorry.
No, you're right. You're right. Then I'll go one step further, and then it's going to be harder to count. That's OK. No, you're right. Good point. Yeah. OK. Now that's P2. But I'm not going to count it this way. OK? Man, you got me. Of course, it shouldn't matter ultimately, but we're supposed to be formal here. OK.
With the center 4 squares, like, you couldn't say they contain a 0 point and the outer ones contain a 1 point at the same time?
What do you mean?
So, like, the minimum of S of the inner 4 squares, you could say that contains a 0 because it contains the boundary. But
well, I mean, yeah, you can.
Contain a 1 at the same time, both contain a 0.
Of course, like the faster way of doing this is to replace it here with interior. Then everything's going to work. But
Yeah.
I didn't define it that way. Okay. This is part of why I'm saying all this stuff is like very clunky. Yeah, it shouldn't matter. Of course, it shouldn't matter. This is part of the. Yeah, it's like there are a couple of choices that we're making to make it work, and then everything depends on the choices we made, seemingly, but they don't really. Okay, that's why I'm not trying to develop this any further. Okay, so now let's count this. Let me try to draw it in even better. Of course, another solution to this would be to say, instead of having a uniform partition, let me push these parts just a little bit by some epsilon so that they don't intersect anymore. You can do it that way too, if you want. Question?
Oh, we're good.
OK. That was 16. OK, how many pixels do we have now? 1, 2, 3, 4, 5, 6, 7, 8. 8 times 8 is 64. 64 pixels. what are the areas? So this is 1, 1/2, 1/4. Area is 1/16. So I'm going to have to adjust it by 16. How many of these pixels hit S? OK. All but 1, 2, 3, 4, 5, 6 multiplied. Oh, we count these, right? OK. All but 3 here. 6, 9, 12. 64 minus 12 is 52. I think this works. OK. We can simplify this, of course. 52 is 13 times 4, 13 divided by 4. OK. So it's better than this. It's not 16/4. It decreased. But it's not 8/4. It's still overshooting. Does this make sense? Now for the lower, we need to count the number of pixels that are completely within S or hit the boundary. Right? It's all but oh, sorry. Even these ones we're not counting. For the lower ones, we should count these guys. Maybe I should have done it using a different color. OK? I'm looking at the pixels that are completely within S. And how many are there? 1, 2, 3, 4, 5, 6 times 4 is 24. Again, I need to adjust it using the size. What was the size? 16. Divided by 4, 6 divided by 4. OK. So again, it's not too exactly, but it got pretty close. OK. Now we keep going like this. And ultimately, you sort of take a limit. Typically, what you would use is this idea that I hope you guys are familiar from 3210 as well. Even though we define these integrals using infima and suprema over the whole space of partitions, insofar as you take a sequence of partitions whose diameters of the diameters, OK, you can compute these using a sequence of partitions such that for each let me just first write it. Let's say you have a sequence of partitions, P sub 1, P sub 2, and so on. To each partition like this, you can look at the sup of the diameters of the pixels. As long as this goes to 0, so that as you're refining along this sequence of partitions, you're really getting more and more resolution. You can just take the limit as n goes to infinity. And it doesn't matter which partition sequence you choose. OK? And so what I mean here is this. That's what I had in mind. How can I sort of make this more general? Say, for instance, for any n, P sub n be the partition into standard boxes of length. What was the length? That was 1, 1 over 2, 1 over 4. At 2, it was 1 over 4. At n, it probably should be 1 over 2 to the n. OK? So that's p sub 1, p sub 2. Why did I choose this? It doesn't really matter. As long as these sides go to 0, I should be able to just take the limit as n goes to infinity to compute these uppers and lowers. That's going to give me a sequence of numbers. And I can compute the lower and upper Darboux sums using these. Meaning, let me write it here. So double star, this guy. This is equal to inf over n, p coming from this particular partition, p sub n, That's what I meant. This is something to prove, but I'm going to leave it to you. This is very similar to the same or similar statement in 3210. The value of doing this, having sort of like a uniform mesh, is that you can sort of simplify this expression a little bit. For this specific p sub n, I know that each of these boxes included, each of the pixels included in p sub n is of the same type, and their volumes are going to be nothing but the square of this. And so this is going to be constant in p, which means I can take it out. 2 to the 2n, and then sum soup of, well, I can just write it like this. So this soup is going to be 1 if this specific pixel hits S, 0 otherwise, which means I can just write it like so. Number of pixels in p sub n such that p intersects S. Now, this is an actionable formula, actually. You can make a computer compute this for you. Okay. Does this kind of make sense? That's what I was trying to do here. Okay. The point here is that in this specific case, the volumes turned out to be this, and the pixelation is rather nice, but it doesn't matter. You can just use a different type of pixelation if you want it. We didn't prove this, but I'm just leaving it to you as an exercise because it's rather standard after 3210. It's the same idea. And if you wanted to write the upper Jordan content, the lower Jordan content of dimension 2, again, we could use the same pixelation like we were doing up there. But instead of counting the number of pixels that hit S, you would count the number of pixels that are completely within S. And you would take the soup. I hope from this perspective, it makes a little bit more sense why perhaps there is still some use in this Jordan content business, especially in the context of Euclidean spaces. You can just, pixelate the space over which you're trying to integrate. And if you're trying to sort of figure out the volume, this would be a very nice way to, a rather sort of actionable way to approximate the volumes from within and without. Okay. And again, you should see that a pixel being completely contained in S is a stronger statement than saying that P intersects S. Right? This implies this, but not vice versa. Which means that this is going to be an approximation from within. It's going to be a lower bound. This is going to be an upper bound. Okay. Now, this type of stuff is very important, really, within the context of things like dimension theory, and especially when it comes to sets that are more complicated. These are perhaps things like fractal sets. It becomes important to be able to do these kind of things. But we're going toward the direction of Stokes' theorem. And there, this is not going to matter that much. So I'm not going to, that's why I feel justified in sort of keeping this a minimum. There are certain technicalities, but there are also sort of different intuitions that you can use to sort of navigate all this stuff. We're just going to fast forward all this. Now, those of you who do want to learn a little bit more about this kind of stuff, I think a good way to, a good place to start would be Terence Tao's graduate measure theory book, An Epsilon of Room. Like in the first section, that's what he covers. And I think it's freely available online. For more. He does discuss all this stuff. We're not going to need too much of this. As long as you're familiar with the standard ideas, it should be OK. Okay. Any questions or comments? Ultimately, it's somewhat tedious, but when you start sort of drawing things and all that stuff, count the number of boxes, it's really nice. It's pleasant. You can just keep doodling things and counting things. OK? We have a couple minutes. Any comments or questions? OK, I think it's a good place to stop for today. Tomorrow we're going to discuss these Fubini and change of variables formula. I'm just going to state them. We're going to be on our way to differential forms after that. Thank you. OK, let's start. Good morning. So today we're going to discuss this change of variables formula. That is to say, U substitution for Riemann integrals, unsigned Riemann integrals that that's what we were discussing so far. No orientation affecting the values, and Fubini theorem. And I think we're not going to prove the theorems. So for the rest of the class, rest of this course, I think it's safe to say you can just take both of these as black boxes. It's not that the proofs are beyond our understanding. We could study those, but it would take time, and they are rather technical. And so I thought instead of focusing more on this Riemann integration, unsigned Riemann integration, it's better to switch over to differential forms, because ultimately I want to spend more time on things like the Stokes theorem. OK, one correction. I mentioned this book by Terence Tao. I called it Epsilon of Room. That's a different book by Terence Tao. So if you want to learn more about this Jordan content business, you should search for his book called Introduction to Measure Theory. If you search this, he has this on his web page for free, so you can have a look, all that stuff. OK, so change of variables formula. What do I need? Let me here draw a picture. I'm going to need two spaces over which I can do integration. So both of these are going to be finite dimensional inner product spaces. Okay. When we're talking about change of variables, remember, for the purposes of calculus, that really means it's a diffeomorphism. There's a diffeomorphism involved. And how do we define diffeomorphisms? We define them between open sets of norm spaces. Is it a problem that these guys, I'm assuming, are inner product spaces? No, because inner product spaces are norm spaces, so they have more structure. Is it a problem that they are finite dimensional? No, it's all the better, in fact. Becomes much easier. Okay, I'm going to have two open sets. I'm going to have one diffeomorphism from M to N. Well, and then I'm going to need, what do I need? I need some sort of subset here over which I can integrate something. That is to say, I'm going to need, let's say, here a subset. Pretend that this phi is something like the polar coordinates. So maybe my subset is something like this. And this really comes from another subset like this. Let's call this subset S, so that the image is phi of S. And on phi of S, I want an integrable function, taking values in the space of real numbers or some other finite dimensional norm space. For simplicity, let's assume that our function is taking real values. So I'm going to have here R. And on this, right, I want a function like this. And what do I want to do? I want to relate the integral of this function over this region to the integral of the composition on this region. Okay, that's the change of variables formula. And so when you think about the assumptions that one could use to make sense of all this, it could go like this. Let's write it like so. E and F be finite dimensional inner product spaces. M a subset in E, N a subset in F be open. Okay. At this stage in this class, whenever you see something like this, you should immediately start thinking about, oh, now there's differential calculus involved, right? So let me let phi 2 be a C1 diffeomorphism from M to N. Capital Phi what is a C1 diffeomorphism? It means, so in the forward direction, phi takes M into N in a continuously differentiable manner. At each point, you have phi prime of x, and phi prime of x depends continuously on x. But I want the backward direction to work as well, okay? That is to say, I want also phi inverse to be defined on all of N output that goes back to M, and likewise, I want phi inverse prime exist at each point and in a continuous manner. That's what a diffeomorphism is. Remember, we also saw this phrase in the context of inverse function theorem, for instance. We said local diffeomorphism there. Okay. Then I'm going to lump a bunch of results in one package. That's what I like doing, especially when I'm sort of black boxing things. So you could say some of these are not technically change of variables formula, but still I think it's good to have the summary. First of all, what do I want to say? I want to say if S is a, let's say, compact Jordan contentable subset of M, then its image is a compact Jordan contentable subset of N. Now, Jordan contentable sets need not be compact, but compactness at this point, you should say, oh, this is a nice assumption. And certainly aligned boxes are compact, so that's already general enough. Okay? And why do I worry about compactness? Why is it a good thing? Because maximum principle holds. Continuous things are immediately, automatically bounded on compacts. Okay? I like that, and that's why I'm going to assume this. You can sort of state more general change of variables formulas, but this is going to be sufficient enough, I think, for us. So 1. For any S subset in M, if S is compact and Jordan contentable, then its image too is compact and Jordan contentable in N. If you're not super comfortable with this idea of Jordan content still, that's perfectly natural, okay? There's nothing wrong with you. But at the very least, you should think for boxes it should work. That is to say, you should be able to take S as an aligned box in M. Its image under this diffeomorphism is probably not going to be a box anymore, but you should say it's still fine. That's a good way to think about it. There could be some distortion, but insofar as the distortion is coming from a diffeomorphism, that's going to be still contentable. That's the first item. Second item, for any compact Jordan contentable set S in M, and for any Riemann integrable function f defined on its image, what we're going to later call pullback, that is to say, f precomposed with phi 2 is Riemann integrable. For any compact and Jordan contentable subset S in M, and for any Riemann integrable function defined on phi of S. If we wanted, we could just instead of R take any finite dimensional norm space. It's going to work that way just the same. For any Riemann integrable function, f composed with phi is going to be Riemann integrable on S. And of course, these are sort of like the preludes to the actual formula. The important formula is this. You get to relate the integral of this guy over this domain to the integral of this guy over this domain, except you have the correction factor, which is the determinant of phi prime. Let me write it the other way around. Say y. Okay, this is this integral. Now I'm doing the u substitution. Okay, u substitution goes back. F composed with phi, this is Riemann integrable. We need more space. Then I have determinant of phi prime at x. I'm going to say a couple of words about what this means in absolute value, dx. Okay. This is part of the theorem. Pretty much anything that came before this was so that this made sense. I sort of wrote different statements that basically says that thing makes sense, and then I wrote the formula. Now, first of all, you should say, well, f composed with phi as part of 2 is Riemann integrable. But here, what we're integrating is not just this guy. It's a product function. But note that, first of all, phi is C1, meaning its derivative is C0. So this is a continuous function. Determinant, or rather the absolute value of the determinant, 2 is a continuous function. So this is a continuous function. In particular, it is Riemann integrable. And the product of Riemann integrable functions is Riemann integrable. Okay? That was probably something that you proved in 3210, and I gave as an exercise in the multivariable calculus case, but it works. Okay? It is true. If this is integrable, by virtue of this being phi being a C1 diffeomorphism, this is going to be continuous, and this guy is going to be integrable also. So this makes perfect sense. What is perhaps slightly more suspicious really is this factor. Earlier last week, we had this issue with defining determinants. And I made a correction, but I didn't discuss how that correction actually rectifies the situation. Okay? And so how do I make sense of this guy? First, I'm going to leave it to you as an exercise. If you have a C1 diffeomorphism between these two open subsets, by definition, phi prime is going to be a linear isomorphism from E to F. So their dimensions are going to be the same. Okay? I'm going to leave that to you as an exercise to go through it. In the context of change of variables, dimension of E is the same thing as dimension of F. There is still a problem because at this stage, even though they have the same dimensions, these are not necessarily spaces of tuples. So to think about this determinant, ultimately I need some sort of a matrix. Even though at this point phi prime of x is a linear transformation from E to F, I really want to think of it as a matrix, as an n by n matrix. And how do you do this? Well, you choose a basis for the domain and the E space and the F space. And with respect to these bases, you come up with a matrix. Then you can compute the determinants, all that stuff. But ultimately, you want some sort of invariance. You don't want this determinant to depend on the bases that you chose. In this case, because our spaces are inner product spaces, they have specialized classes of bases. These are orthonormal bases. Okay? And so this is the first part of the exercise. Second part of the exercise, how determinant of phi prime of x is defined. Technically, at this stage, this determinant is not well defined, but its absolute value is. Okay? So here's the idea. Let beta be an orthonormal basis of E and gamma be an ONB of F. And what was an orthonormal basis? This means that beta is a tuple of vectors in E. Each of these vectors in this tuple has norm 1. They are normalized. And in fact, and furthermore, if I were to take any two basis vectors here and take their inner product, that's going to give me 0. They're going to be orthogonal. Okay? These are the special types of bases. You had shown in a previous, in problem set 2, I think, that any inner product space, finite dimensional inner product space, has this, essentially by way of this Gram-Schmidt algorithm. Then writing our diagram, we have here this. Let's say that they have the same dimension, which is n. So this beta chart gives me an isomorphism from E to Rn, and gamma chart gives me an isomorphism from F to, again, Rn. And if I were to look at the matrix representation of this linear transformation relative to these two bases, that gives me a honest to heavens n by n matrix. Which we denoted like so. Okay. Certainly, this determinant should be related to the determinant of this, which you should be able to compute using 2270. But the point now is that you want this calculation to be independent of your inertial frame of reference. From a physical point of view, these bases are those, really. These are inertial frames of reference. So if you were to switch beta to, let's say, beta bar and gamma to gamma bar, okay, let me write it over there, actually. We had also studied in problem set 1, I think, how these changes of bases really change these matrices. So are another pair of O and B's. Beta bar is an alternative for beta, and gamma bar is an alternative to gamma. I want to relate the matrix representation of phi prime at any point x relative to these new frames. I want to relate that matrix to this matrix. Now, this is how it goes. Okay. This is the matrix representation of the identity transformation of, if you want, F. That corresponds to going from gamma to gamma bar. Then you have here this. Then you have here this. Okay. The point of doing all this is that by virtue of the fact that both of these bases are O and B's, this matrix is going to be orthogonal. Let's call this P. Let's call this Q. These are orthogonal matrices. Do you guys remember what it means for a square matrix to be orthogonal? We should have learned this in 2270. So for instance, something like a rotation, right? It means if you were to take the matrix and multiply it by its transpose, you get identity. In particular, determinant of a matrix is the same thing as the determinant of its transpose, and determinant is multiplicative, which means that by virtue of the fact that P and Q are orthogonal, their determinant can be either +1 or -1. Cannot be anything else. Okay? Which means that if you were to take the determinant in this equation, determinant is multiplicative, you would get here 1 determinant and then 3 determinants here, but these two factors would be plus or minus 1. If you were to take the absolute values, you would get the same thing. Okay? That's why you could say determinant of phi prime at x in absolute value is a well-defined number, which is this common value. Determinant of this in absolute value. This is well-defined and independent of O and B's, beta and gamma. What is the exercise? The exercise is to go through these again and convince yourself that these really work the way I mentioned. Okay. Again, let me reiterate. How can we think about this? Well, we talked about how, essentially by definition, there's a change of variables formula when your phi is a linear isomorphism. We just looked at boxes, but it doesn't really matter. You should think if something works for linear transformations, it should work for C1 diffeomorphisms. This is not always correct, but it's correct rather often. Okay? If something works at first order, it works for the whole thing. Right? So C1 diffeomorphism, in principle, you should think, well, okay, so it's a linear transformation, but maybe there are higher order correction terms from the perspective of Taylor. But integration is a first order thing. So for it, it doesn't matter that there are higher order correction factors. Okay? Why would that be the case? Because ultimately these integrals are defined by virtue of partitioning the space over which you're integrating things. But then if your pixels are small enough, your diffeomorphism is going to be virtually linear by virtue of mean value theorem, whatever. Okay? Does this make sense? Now, proving this, it takes a while. Okay? It is a nice exercise, really. It's a nice theorem to prove, but I am happy to sacrifice that for differential forms. Okay. Any comments or questions about this? So this is the first part, and this is really one of the main tools that you use typically to compute integrals in multivariable calculus, of course. Later on, once we switch over to differential forms, we're going to define their integrals so that essentially this works. Except there, we're going to need to sort of get rid of these absolute values and make sense of determinants without this issue of plus or minus. To do that, we're going to need to fix a certain orientation on these spaces. We'll get there later. So these are unsigned integrals. When you do a change of variables, the integral changes according to the absolute value of the determinant. This is always a positive factor. Okay. And this is really what makes this theory unsigned Riemann integrals. Okay. How do you determine? You look at how things transform. You look at the law for transformation. Under change of reference frames, or nonlinear reference frames in this case, how does the integral, how does your values change? If it always changes with respect, using a positive number, that means it is unsigned. It doesn't matter. Because in principle, what you could do as your phi is you could just flip, right? You could reflect whatever. Under reflections, this value would not change, for instance. You should think of it like that. OK. So that's the first part. Second part is Fubini. I want to discuss that as well. Again, I'm not going to give the proof. Now, part of Fubini is partial integration. Okay, I want to take a multivariable function and integrate this function relative to only some of its variables. Remember, in differential calculus, partial derivatives were kind of cumbersome to deal with. In integral calculus too, there's a similar thing happens. And Fubini theorem, no matter what the integration theory is generally rather technical. Okay, you always want to have a Fubini theorem, but almost always it's one needs to be careful about. Okay, Fubini. Okay. We can state it for vector-valued functions as well, but let's keep it simple and define it, or state it for real-valued functions. Let V be a finite-dimensional inner product space so that I can do integral calculus on it. S be Jordan contentable. Yeah. And let me let f be a Riemann integrable function defined on S, taking real values. I want to assume that V is of the form V1 times V2. I want to have a predetermined horizontal component and a vertical component. If you want, you can pretend that V is just R2. And I have the horizontal axis and the vertical axis. It doesn't matter. Suppose V is of the form V1 times V2. And when I write it like this, I really mean also, because these are supposed to be inner product spaces, any vector in this direction is orthogonal to any vector in this direction. Okay. And S is of the form S1 times S2, where S1 and S2 are Jordan contentable in V1 and V2. then let's write it like this. What do I want this time? Let me again draw a picture here. Actually, let's leave this and draw the picture here. Okay, this is V1, this is V2. I have a product set. I'm just going to pretend that it's a box, of course. This is my S. This is S1. This is S2. And I have an integrable function. I have an integrable function defined on this box. I would like to relate the integral of f on S to iterated integrals. Let's write it like this. Okay. What do I want? I want to take a point. Let's call it x1 in S1. And I want to look at the corresponding slice in S. Now it's going to be a vertical slice. Okay. Now, if I were to fix x1 itself, it turns out how do I want to say this? Let me first write the formula. x1 goes to, what do I want to do? I want to integrate over S2 of this guy. Yes. I fix an x1, I look at the slice, and instead of integrating my function over the whole S, I want to integrate it over this slice. This slice is a copy of S2, but on x1. Okay? So in this expression, I'm thinking of x1 to be fixed and x2 to be the dummy variable. Once I integrate this, it's going to be a function not of x2, but x1. Okay? Now, the problem is that this function for fixed x1 need not be integrable. So this integral may fail to exist. But if you were to look at lower integrals, for instance, then this becomes integrable. So let me write it like this, as well as x1 goes to the upper integral of f of x1, x2. These are both Riemann integrable functions from S1 to R. Integrable. Well, I guess I'm going to have to delete it. Similarly, of course, instead of fixing an x1, I could have fixed an x2 and looked at an integral over a horizontal slice like this. The lower and upper integrals of such functions obtained are also integrable. Lower integral over the horizontal slice at height x2 and x2 goes to the upper integral over the horizontal slice are Riemann integrable. And 3, of course, the integral of f is equal to the integral of any one of these functions. Which we could write like so. Integral over s of f of x1, x2, dx1, x2. Let me just write one of these for simplicity. This is the lower, like this. dx2, okay, now that's an integrable function inside, defined on S1. I want to integrate this over S1. Over S1, upper integral, over S2, f of x1, x2, dx2, dx1. And there's nothing special about this order. You could switch the order as well. We can apply the same thing here too. I'm not going to write it. Let me just write it like this. S2, S1, S2, S1. Okay. And this is one of the things that makes it very useful. You get to change the order of integrations. It's a pesky matter, and this is one of the reasons why this theory is not really nice for integration. Ultimately, when you have iterated integrals inside, you don't want to be worried about these inner integrals not existing. This could happen. It could happen that you have a function that depends on two things, that is integrable, but is not integrable as a function of one variable. Riemann integrability is not a very nice property to deal with. I'm going to leave it to you as an exercise. That's a very nice exercise, actually, to come up with an example. So find an f, let's say defined on a box, in fact, such that at least for some, let's say, x, it is not integrable. So y goes to f of xy is not Riemann integrable. Okay. Again, reiterating, Fubini theorems, even in this better integration theory of Lebesgue, whatever, is rather technical. It's very useful, but takes a while to establish. One needs to be careful. Certainly in the case of Riemann integration, one needs to be careful. One perhaps nice situation where you don't need to worry about these lower and upper integrals is, well, if you can somehow come up with a function such that each slice 2 is integrable, that would be good. In particular, for instance, if f were continuous, this would work the way you expect it to, because if f is continuous as a function of 2 variables, it is also continuous as a function of 1 variable, which means that it is also integrable on each slice. Okay, in that case, it becomes slightly better. So maybe I'll write it here. I'll write it here. Of Fubini, we need to assume, let's assume again this S is compact so that things work nicely. Say S is compact and Jordan contentable and F is continuous. In this case, things work rather nicely, which I think is going to be sufficient for us as well, because the differential forms we're going to be looking at are not going to be worse than continuous. Okay. To just cut down on the technicalities, even though technically you could think about Riemann integrable differential forms as well, and beyond that, probably we're not going to do that. Okay. Yeah, ultimately, maybe I should say this, the reason why things are sort of complicated in the context of Fubini is that the notion of volume changes dimension. Right? You start with an essentially two-dimensional integration. So here, where is it? In this expression, this d implicitly involves a two-dimensional thing, whatever dimension means in this case. Whereas these two d's include one-dimensional information. And so a lot of things can get beneath these two things. Okay. Again, I'm not going to give you the proof. I think you can just black box this Fubini as well as the change of variables and take them as computational tools. Later on, once you take a class, those of you who are going to take a class in measure theory and stuff, you're going to have to go through all this and prove them in the much more sort of pleasant context of Riemann Lebesgue integration. Okay? Any comments or questions about any of these? Okay. I was thinking of starting differential forms proper. We have a couple minutes. Maybe I should just say a couple words, because I wanted to mention this global perspective. Remember, so now we're going back to differential calculus, okay? Differential forms, even though they are going to be ultimately things we're going to integrate, fit really well into the context of differential calculus. And we're going to keep the use of integral calculus to a minimum. If anything, we're going to be often integrating things that ultimately end up as integrating over boxes. It's not going to be rather complicated. And so the global perspective with differential calculus. The idea is this. Let's start with a C1 curve in some space F. Well, we can take it to be a finite dimensional norm space, whatever. We would like to imagine this, or rather its image to be a subset of F, right? And here is the space of parameters. I think of that as time. And gamma is a function. At each time, t, gamma of t gives me a position. And we wrote gamma prime of t, if you follow the definitions, it's going to be just a vector at F, in F. But really, I want to tether that vector at this specific point. In physics land, they call this a point or position-bound vector. So somehow, even though this is a vector, I don't want to imagine it here. I want to imagine it attached to this point. So the global perspective is all about managing this attachment from here to the, instead of attaching vectors here, to the correct points where they should be attached. Okay, that's all I'm going to say. We're going to continue tomorrow. Thank you. Okay, let's start. Good morning. So today I'd like to switch over to differential forms. But before that, I thought it would be a good idea to discuss just a little bit something that I had mentioned a long time ago, namely this global perspective to differential calculus. I told you a long time ago we're always focusing on functions defined between open sets of norm spaces, and that is like special relativity compared to general relativity. And so I'd like to just give an idea as to how one sort of generalizes to a more global perspective. Ultimately, I hope, even though we're not going to use it in the context of differential forms, I hope it's going to make things a little bit clearer, even though we're not going to necessarily use these formalisms. Okay, so let's go back to the standard setting that we're used to. I have open subsets in normed spaces. In normed spaces. I'm going to define things like tangent space and tangent bundle for these guys, and that's going to give some sort of semi-global perspective. And I'm going to try to give you some sense as to why I would want to do this. And then we're going to try to sort of tease out what the global perspective should entail. In particular, we're going to sort of try to come up with a definition of a manifold, a space on which you can do calculus. Okay. The main idea is this, behind this semi-global perspective, and that's what I was discussing at the end of last class. In our formalism so far, we can do things like, well, we can take a path in some space. Okay. let's say I'm just looking at this part. Okay. And often, when we were really sort of trying to come up with statements and proofs, we were thinking of the following. We would take a time parameter here, t. Gamma of t was a point. Okay. And gamma prime of t, using our definition of the derivative of a function at a point, in this case, reduced to nothing but a vector in E. Okay. The formalism gives us this. But when we were really trying to use this formalism, I didn't put this gamma prime of t to be an arrow. I never thought of this as an arrow starting at the origin in E. The origin was irrelevant. I attached it here. Okay. Oh. Let's draw it a little bit more accurately, like so. And for most purposes, it was fine, at least for functions defined between open subsets. But ultimately, this formalism allows me to do things like, well, technically, this makes perfect sense, assuming that gamma prime exists. But from a more sort of intuitive point of view, gamma of t should be a position type quantity, and gamma prime of t should be a velocity type quantity. So you should not be able to add these up. Okay. So sometimes, you see, being able to do things mathematically makes things actually more complicated. And so the point of what I'm going to do now is going to be to soup up the formalism so that now this is not allowed. Okay. And how am I going to do this? Well, I'm going to think of M as a space of positions. In physics or engineering, this is what is called a configuration space. Okay. So space of positions or configuration. Space. I would like to define something else that is more complicated than M and N. And these I'm going to denote by Tm and Tn. I'm going to call these the tangent bundles of M and N. And now these are going to be what are called phase spaces. These are going to include not only position information, but velocity information as well. But they're going to be so that this is not allowed. Okay. So for each x in M, define the tangent space of M, tangent space of this open subset itself. Okay, at x to be, well, I'm going to denote it like this: capital T sub x next to M. This is a standard notation. So this is something like the infinitesimal version of M at x. I'm just going to define it to be this larger set, larger norm space. Okay. Of course, really, there is something really bizarre going on. Ultimately, you should say left-hand side depends on the base point, right-hand side doesn't. And here, I'm really using this idea that M is a subset in E. So how can I think of this tangent space at this particular point without directly referring to E itself using calculus? Imagine now, that is to say, that you don't know that M is a subset in E, but you can do calculus. That means that you can, again, take curves in M that passes through one point. If you can talk about differentiable curves in M, that means you can talk about their primes. And so you can define Txm to be the velocities of all curves passing through X. So gamma prime of 0 such that gamma is a C1 path in M, and at time 0 it is at X. If I didn't know that M is a subset in E, but still somehow could make sense of this, I could just take a bunch of paths. So this is what I'm doing, really. Not even going to draw these coordinate systems. M is now just a blob, just like floating in sort of abstract matrix space. Imagine in the matrix there's like this white environment. Imagine it's something like this, like a blob. But you can still take a point. It's a set after all. And somehow you can take paths that pass through this point. And imagine somehow you get to talk about what it means for these paths to be differentiable. If you can talk about what it means for any one of these paths to be differentiable, you can talk about their derivatives at this point. The collection of all such derivatives is going to be the tangent space. Okay? So now you're not referring to the idea that M is a subset in E. Does this kind of make sense? You see, this was like a common pattern in this class. We had like a bunch of things defined, and then we sort of kept so we have, let's say, a bunch of concepts defined, intuitive, whatever. We kept the remainder the way they are, and we upgraded these so that the remainder still work the way they do. And then we sort of like kept upgrading each one of these. That's sort of like what we're doing too here. Another way to think about this is that, so this is like a more geometric way of thinking about the tangent space at a point. Another way to think about it is, well, it's the space of all directional derivatives at X. Directional derivatives as operators acting on, let's say, scalar valued functions. And so I can say this is also the space of all, how do I want to write this? Just write capital D. Capital D. Let's write it like this. Capital A. It's going to be a bounded linear transformation on the space of, let's say, infinitely differentiable functions. We can do 1, 2, actually. Let's do infinitely differentiable functions, taking real values. Okay. Now, A takes a function that is scalar valued, and it should be something like a directional derivative, meaning it's linear, okay, and it has to satisfy the product rule. I think, mention this, but directional derivatives, the way we define them, do satisfy the product rule. Namely, for any f and g, infinitely differentiable, assuming we know what this means, I want a of fg to be the same thing as af times gx plus fx ag. the technical name for something like this is a derivation. It's a linear transformation, bounded linear transformation that satisfies the product rule. You can think of it like this as well. Assuming you know what these mean, okay? Or if you like differential equations more, you can think of this as the space of all first-order linear operators, linear differential operators on M. You can think of it that way as well. So this is the tangent space. And now I'm going to define the tangent bundle. Okay? And the tangent bundle is going to be nothing but all of these put together. At one point, at each point in M, I'm going to have one tangent space. I'm going to put them together. Let me write it here. This was a definition of a tangent space. It's a vector space. It's a normed space, in fact. The tangent bundle of M is Tm. So I'm not now specifying the base points, and it's going to be nothing but the union of all of these guys. In our case, of course, each of these tangent spaces I can identify with E using this fact. And in our case, this is nothing but M times E. Okay. So M, you see, keeps track of positions. It's the configuration space. On the other hand, Tm keeps track of both positions and velocities. This is what is called the phase space. Phase space. There are many other phase spaces, but this is the standard one. Now, if I have a function differentiable between from M to N, let's call it f, in this semi-global perspective, I have an associated map between the tangent bundles. That I'm going to call it TF. CK from M to N. The tangent map of F is TF. It goes from one tangent bundle to the other one. And how does it work? Well, in order to, so any point here is a position together with a velocity. So you feed to it an xv, and it gives you back f of x. So it has to transform the position according to f, and it has to transform the velocity according to f prime. One benefit of this, for instance, is that this notation keeps track of base points, let's say in chain rule, for you. Meaning, in this notation, if you have two functions that you can compose, We just write it like so. So t just distributes over functions. Okay. For us, it's not that important, of course, because we were just looking at functions between open sets. I'm just trying to give you a sense as to how things sort of develop. Any questions so far? Part of why I'm sort of trying to develop some sort of global sense for differential calculus is that as opposed to differential calculus, integral calculus by nature is something global. There's no such thing as a function that is integrable at a point. Okay? So these are fundamentally different operations. And since ultimately, therefore, fundamental theorems of calculus too are of global natures, I think it's going to be good to have some sense as to how differential calculus at large works. And so I had defined before a vector field on M to be nothing but a function from M to E. Okay? But again, if I were to think of a vector field like that, for any x in M, I'm going to have a vector, but I want that vector to be tethered at x. So that means that the vector field really is not quite a function from M to E, but it's a function from M to Tm. This is still not the global perspective. Okay. On M is a function, let's call it capital V, from M to Tm, such that for each x in M, getting resonant here. Okay. V of x, well, I want it to be a vector tethered at x, which means that this guy has to be in this specific tangent space. Okay. A C1 vector field, C2 vector field, these are all defined in terms of the regularity of this function. And note that Tm itself is an open subset in some other norm space, namely E times E. So you can talk about what it means for this guy to be Ck, C infinity, whatever. And while we're at it, let's define a differential one form as well. As opposed to looking at velocities to get the phase space, you define what is called the cotangent space. Then it gives you the space of positions together with momenta. Okay? And instead of looking at Txm, I'm going to look at the space of linear functions from this to reals. Cotangent space of M at x is, this is typically denoted by T upper star. So space of bounded linears from Txm into reals. Cotangent bundle is the union of these. T star M, like so. We didn't talk about this that much, but there's again, if you have a function f, you have an induced function at the cotangent level. Let's not get there. It's not going to be important. We're going to use it ultimately, but I'm not going to keep using this more sort of semi-global perspective for differential forms. We're going to say it's like the pullback. We're going to use that word later. And so let me write this. This is the space of positions and momenta. And much like a vector field on M is a function from M to Tm, a differential one form is going to be nothing but a function from M to T star M. We're not going to use this notation because after today, I'm not going to mention that much about these cotangent spaces, tangent spaces, and so on. We're going to go back to the standard definitions, so I'm not going to write it down. But that's what's going to happen. Any comments or questions so far? OK. Now, global perspective. Ultimately, if I can come up with a function, come up with a set M on which I can talk about differentiable things, I should be able to define the tangent space, tangent bundle. It's what is called dual space, T star, and then cotangent bundle. Everything should work, should go through. So the point is to figure out what it means for a set to admit differentiability. How can I make sense of this? Well, I'm first going to stick to this case. Let's remind ourselves what it means for f to be differentiable. At x, let's say, right, we had to write this limit. I'm back to the standard case we're used to. If there is a bounded linear, lambda, between the norm spaces, such that a certain limit is 0, right? I need to compute this guy. Let me write it bigger. I look at this ratio, and as h, which is a vector in E, goes to 0, I want this limit to go to 0. Do we remember this? This is one of the most important things that I hope you learn from this class. Of course, eventually we figured out that this lambda, capital lambda, we denoted it by f prime of x. It's a bounded linear transformation from E to f. It's unique, whatever. What else did we learn? All from the perspective of Taylor, I'm saying that f should have a first order Taylor approximation. From the perspective of Taylor, that's what differentiability is. Approximately. OK. Now, I want to sort of turn this. I want to try to reinterpret this so that it makes sense in a much more general setting. Say now, let's forget that M and N are open subsets in normed spaces. Instead, well, there's going to be a limit ultimately again. Let's just say that these are metric spaces. Say that they are just metric spaces. So you can still talk about continuity, okay, convergent sequences, whatever. But some things in this expression now break down. Now I should ask you, if I relax my assumptions on m and n in this expression, what are now suspicious? What symbols?
Metric space doesn't guarantee that we have a norm.
That's one. So the norms are suspicious. But in a sense, you can say, well, I can say, instead of this norm, I can look at the distance between this guy and this guy, for instance. And here I can say, oh, this is nothing but the distance of h to some predetermined point. What you're saying is correct, but there is something more important that breaks down in this expression. Any other guesses?
I mean, the limit isn't guaranteed to work because
The limit is okay. I mean,
Oh, okay.
sure, but ultimately, assume that I replace these norms by metrics, so it's a number divided by number that I can take the limit of, okay? H goes to 0. Okay, it's going to be a predetermined point. It's not really an issue. There is something more important that breaks down in this expression.
Just guessing the capital lambda?
That's a good choice, but I want to still keep E and F. Okay, these are going to be, ultimately there's going to be some sort of linear space underneath. But in this expression, what else could be suspicious? You're almost there. I want you to think about this because even though we're not going to discuss this any further, once you see the definition of a manifold, after you think about what goes wrong here, it starts making a lot more sense. Okay? What breaks down?
Metric spaces don't necessarily have a point that you call 0.
Sure, yes. But I can just fix a specific point. That's true.
We're running out of things that can break.
Let's remind ourselves. A metric space is a set together with a notion of distance. Okay? So there is something extra there in that expression. It's the plus and minus. This is the main thing. Okay? Does this make sense? In a metric space, you cannot add things. Adding, subtracting, these are vector things. Okay? Imagine, like, if I were to take, well, if I were to take, where did I write this? A function from m to n, that's a metric space, we said, with the ck metric, whatever. But if I were to add two such functions, you might get out of this set. So addition is not really defined here. It's still a metric space. You can talk about distances between functions, but you cannot necessarily add them in general. But still, what you say is, I still want to make sense of this plus and minus. And the redeeming point here is that you don't need plus and minus in this expression, vector addition and subtraction, to make sense for any h whatsoever. You need it to make sense for small h. So a metric space is nothing but something, a manifold is nothing but a metric space such that for nearby points, there is an addition and subtraction. So for nearby points, somehow some vector space structure kicks in. That's all you need, right? Because you're going to take the limit as h goes to 0. You don't need this plus to make sense for h very large. It does make sense in our case, but it doesn't say anything by way of Taylor approximation. Taylor works only higher order terms, up to only higher order terms. Right? Now, how do you do this? You say, then, and a manifold is a metric space together with a bunch of open sets, each of which is homeomorphic to an open set in some normed space. Let me write this down. A CK manifold is, let's start like this. First you fix a local model. That's going to be your linear space, okay? Let E be a normed space, and K, as before, could be 0 actually, or infinity. A CK manifold locally modeled after E is a metric space M together with a family of what are called charts. These are denoted by U sub I, phi sub I. Such that each of these U sub i's is an open subset in M. That makes sense because M is a metric space. And I want the union of U sub i's to contain all of it, to be everything. Phi sub I to be a function from U sub I to E that is homeomorphic onto its image. Phi sub I is a C0 function, continuous, into your model. That is homeo onto its image. So these are local charts. It's almost like a basis, but nonlinear bases, imagine. The third property is, so that you can do things in an invariant fashion, is what it's called. If you have two charts that work for, let's say, the same point, I'm going to draw a picture in a second, I want them to be compatible in the CK manner. That is to say, for any ij, I want this to be CK. Okay. It's a mouthful. I'm just going to rather draw a picture. The picture is more important. So now my M is the blob. Okay. It's not inside a larger space necessarily. Perhaps a better way to think about it is that it's an object that you can see only locally. It's almost like there's like fog of war. Okay. So you cannot see the whole thing. You can only see small patches. Whenever you look at a small patch of it, you see an open subset of a norm space. You don't like it? You like it?
I don't like any of this.
Okay. Well, I'm not going to ask you to compute things in this generality. But yes. So I have here one open subset and another open subset. Okay. Openness I can make sense of in metric spaces. But somehow I have this chart, phi sub I, that tells me that this is nothing but something I know how to deal with. Okay. Okay. And I have another chart here. Some other open subset. So if I had a function into something else to see if it is differentiable, ultimately I'm going to use this. But how I'm going to use it is, well, I'm going to take a point x here. I'm going to use my chart. Look at the atlas. It tells you that, oh, in this map, this is where things are. Okay? This point in this metric space, let's say, gets to this point. You do the same thing in the output space as well, but let's not worry about that. And ultimately, once you have something, once you have an open set in a norm space, everything we learned kicks in. The problem is, this is not exactly the thing itself. There's a transformation that you applied. So you need to make sure that whatever you did was independent of this specific map that you used. So you say, oh, if I were to use a different map, ultimately, things should be the same. Because otherwise, how do you know that the thing that you computed, the thing you said about f, is really because of f and not because of how you measured things? Okay. And I'm saying this third property essentially allows you to say, make sense of this in a consistent manner. So that means that just like in linear algebra, we have abstract, let's say, finite dimensional vector spaces. And typically, if you want to compute things, you take bases, reduce everything to matrices, compute this, that, and the other thing. But then you want to say, if I were to change the basis, first of all, there's something called the change of basis matrix, whatever. So you want that, okay? And you also want to keep track of how whatever you computed changes when you change the basis, when you change your inertial frame of reference. This is essentially the same idea. These charts are nothing but choice of bases. So in a sense, these are approximately these m sub betas we were using all along for linear spaces. The difference, though, is that in the case of a vector space, which is this bizarre thing, right? We have this bizarre, mysterious vector space, apply m sub beta to it, it turns into something you know. This is also similar. M is this bizarre thing, apply one of these charts, turns into something you know. Except because this M is possibly nonlinear, this chart that you used doesn't allow you to make sense of every single thing. Its scope is very limited. And a big part of global perspective, global analysis, or global differential calculus is to learn how to figure out what these charts do and manage them. Okay. Does this make sense just a little bit? Okay. So this is, manifolds are really the modern context in which one does calculus. But it requires, so I gave these definitions, but already this definition itself is a mouthful. It takes a while to get accustomed to. And ultimately, how we have any hope of discussing differential calculus is, instead of looking at this global perspective, we just focus on the local perspective. We just focus on what happens between open subsets of norm spaces. Then you don't have any of these issues. So in a sense, by focusing on differential calculus for functions defined on open subsets, or we're putting you in the seat of a general. There's a war going on, and you see the whole thing. Okay. The global perspective is you only see what happens near you. Okay. Okay. Oh, there's still time. So that's that. I just wanted to mention that some of you are interested in this business. It's not going to matter too much for us. Certainly, I'm not going to ask you to these kind of things. But once you get used to this global perspective, figuring out how things should operate become a lot more intuitive in my experience. And now we're going to switch over to differential forms. I have a couple minutes. One thing I want to say about differential forms is that there are 3 different perspectives that I think are going to be useful when it comes to differential forms. And I really want you to understand this. And as far as my calculations are accurate, we have, after this class, 10 more classes left. And so again, I'm going to focus on the intuition and understanding. And if that means that I'm going to have to sacrifice proofs, I will go there. Okay. The 3 perspectives that I think are useful in the context of differential forms is, 1, it's something syntactic. It's a bunch of rules. You just operate based on them. Second is the perspective coming from differential calculus. We're going to be, so you guys are already somewhat familiar with this, in fact. There are going to be families of alternating multilinear forms or functions. And third is going to be the integral calculus perspective. We'll discuss all 3 of these perspectives and somehow put them together to the extent we can. Okay, thank you. I'll see you on Friday. Okay, let's start. Good morning. So today, we're going to really switch over to differential forms. Before that, though, I wanted to make a couple more comments about manifolds. I'm not going to ask you anything specific about these things. It's all you need to know, I think, it's sufficient for this class, is it's differential. It's the true context of calculus, where you get to do this differential calculus, but from a global perspective. And a manifold is basically something that you cannot see completely. You can only see parts of it. And each part, whenever you look at it, it looks like an open subset of a norm space. Okay, let me remind you. Is something one can't see completely. One can't see quite possibly. Sometimes you can. Something like a circle is certainly a manifold, but typically you can't. And even this comes with a caveat. And any part of it that you can see is an open subset of some norm space. Open subset. Normed space. So the local theory works pretty much the way we discussed, but then it becomes a problem. How are these parts put together to complete this whole thing that is the manifold? Okay. Now I want to ask you, do you have any guesses as to how old this idea is?
How old?
Yes.
Didn't Riemann come up with this? So he talked about curves over n-dimensions.
Say again?
Riemann?
Yes. Nice. Surprisingly, this is not any newer than the notion of the Riemann integral. Of course, the Riemann integral itself is 200 years younger than the fundamental theorem of calculus, somehow.
We have integrals before Riemann.
Well, people kind of thought, you know, it should mean, you know, the area underneath the curve, whatever. In fact, people typically attribute the proof of the fundamental theorem of calculus to the advisors of Newton. So actually we had a proof of the fundamental theorem of calculus because before calculus when it was invented, surprisingly. But of course, you know, 100 years later and stuff like that, it's like everything gets recontextualized. And we start telling the story. Oh, you know.
Yeah.
And in fact, what we're discussing as a proof was something that was invented in the beginning of the 19th century, too. Especially in undergrad math education, I feel like because we don't mention these kind of things, we give the wrong impression as to how math is operated, how math is done. It works backwards, you see, somehow. Yeah, so the idea of a manifold goes back to Riemann. So it's a very old idea. And indeed, if you dare to think of it from a more sort of intuitive point of view, that's how we think about anything anyway, right? So it's like with babies and stuff. You sort of like do this, and then you do that. The babies don't know that when you do this, you're still there, right? It's like they think, oh, you cease to exist. Or, you know, like I do something like this, and oh, that's a face. And then you hide it, and the baby is like, oh, it's gone. It ceased to exist, but now you know, we learn. All of us know that what really happened is that now you can't see it. It's still there. It's a very basic idea. It takes for us humans to understand that this is how reality works a long time. And even though math is a lot simpler than reality, it's still not as simple as taking into account situations like this. Okay? And this manifold, again, is part of the standard toolbox of a modern mathematician. So those of you who are going to advance into more technical, more complicated courses, eventually you're going to have to learn manifolds and how to sort of do calculus within these contexts and stuff like that. What else do I want to say? Yeah, so we were talking about differentiable proofs. So somehow I would like to say something like math itself is something like a manifold. And even in this class, if you think about it, we have these different charts. One chart is what is described in the textbook, and another chart, you can say, is what we're discussing in class. I'm actually saying the same things, like we're covering the same topics. But from one chart to a chart, so if you change your chart, the same thing, same mathematical object, it looks different. Okay, it feels different. Even when we have sort of f, right? When you see f, you think of a function. And when you see x, you think of an independent variable or a dependent variable. But in a different situation, maybe x, if you write it a capital X, now this is a function. It's what is called a random variable. From a different context, maybe this is a vector field. So we are, in fact, doing math in this sense as well. The caveat here is that this idea has been around for a long time, and pretty much since the 60s, even the notion of a manifold has been becoming a lot more, inconvenient. It becomes not expressive enough. So now people are looking at generalizations of manifolds. They have more bizarre sounding words, things like orbifolds or varifolds, or more generally things like locally ringed spaces. Now it becomes more algebraic. So that's one. These are just phrases for you to just think about in the back of your head. So orbifolds, varifolds, etc. So even this notion of a manifold is not enough often for modern purposes of mathematics, and some people who are using mathematics. On the other hand, it's still useful. There is something called manifold hypothesis. Did you guys hear this? This is something that people in big data like to use. Manifold hypothesis. Now, I have a couple friends who are doing research in AI and and getting paid a lot, all that stuff. And depending on the day, if I ask them, some days they say, oh, this is pseudoscience, and some days they say, oh, there's something to this actually. So everything with a grain of salt. But the idea here is, when you hear the word manifold, at least in the context of big data, you want to say things like, or you want to think something like this. The fact that on a manifold you get to do calculus essentially says that a manifold is a sign of low complexity, whatever that means. In a big data context, you have a bunch of points. Maybe I should have done it differently. You have a bunch of points, that is sampled from something. And these are discrete and stuff. But the idea is that really, even though at first glance these data points, these samples, look like they're random, they are not really random. What is really happening here is that underneath there is a manifold and of lower dimension, and you're really sampling these points within that manifold. That's essentially the manifold hypothesis. Okay? And in a sense, you can think of something like the implicit function theorem as sort of an indication for this as well, right? Because in the implicit function theorem, remember, we started with something like this. We started with a function that took, let's say, two variables. Initially, these variables are independent. Both of them are independent variables. But somehow, the moment you fix the output under mild assumptions, right? So the second derivative has to be invertible, whatever. The moment you fix the output, there is some sort of dependency created between these, conditionally speaking. Okay? So you can think of implicit function theorem as something that points towards this manifold hypothesis. In other words, things that do seem random are maybe not random that much. But of course, if you want to use it in the context of differentiable proofs, certainly mathematics and the way we do math should be more complicated. So probably one should call this a post-manifold hypothesis. So the collection of math, or math itself, is something more complicated than a manifold, but there are certain ideas that are relatable or related in this context. Okay. What else do I want to say? Okay. Let me say two more things. This star, I say typically, but people, after they defined this notion of a manifold, they realized that in fact, even these abstract manifolds can be considered as subsets of some norm space, at least for finite dimensional. So if your local model is Euclidean, and at least if the manifold is compact. These types of theorems are attributed often to mathematicians like Whitney and Nash. So there are theorems like Whitney embedding theorem and Nash embedding theorem. So these are two different works. Any manifold is essentially a subset of some Euclidean space. So in a sense, you don't need this abstract formalism. So any compact finite dimensional manifold is a subset, or can be considered to be some subset of some Euclidean space of very large dimension, possibly. There are certain dimension bounds, but let's not get there. To be a subset of some Euclidean space. Meaning Rn. So you probably haven't heard of Whitney, but maybe you have heard of Nash. He actually got a Nobel Prize in economics for something that is a lot less significant, is what a lot of people would say. compared to this. But yeah, so there's this film, A Beautiful Mind. And who's the actor who plays him?
Russell Crowe.
Yeah, right? The Gladiator. Yeah. Okay, so, and let me just say this too. So these two are very different things. So Whitney only keeps track of the smooth structure, so differentiability. Nash keeps track of the metric structure as well. So it's a lot more complicated, really. And the way Whitney did it is essentially by Taylor approximation. With Nash, it's essentially implicit function theorem. But he did it in a more general setting, more complicated implicit function theorem, more sophisticated, all that stuff. So I'm not going to write these down. But I think as a first approximation, it would be good to say Whitney embedding basically uses Taylor, and Nash embedding uses implicit function theorem. Okay, which implicit function theorem later on turned out to be important in the proof of the Poincare conjecture. Anyway, so you see, multivariable calculus is very useful. It's like for applications, but for math purposes as well. People who are very good at calculus, they can actually do things, a lot of things. Okay. Finally, I wanted to mention this textbook. I suggested this to some of you, Loomis and Sternberg, Advanced Calculus. This is, in fact, one of the textbooks that are textbook references. And I've been using parts of it throughout this class as well. It's more advanced compared to what we're doing. But if you're interested in this manifold setting and stuff like that, I think this is a very good place to start. It's freely available at Sternberg's webpage. Sternberg is also one of the great mathematicians. Okay. Any questions about any of this? This is just like some factoids, some things, some ideas for you to think about. Not really anything I can ask you to regurgitate later. So differential forms, this is the final sort of stretch, okay? This is where everything that we discuss in this class are going to come together. And in fact, more things also. There are three ways to approach differential forms, okay? And I think all three of these are going to be useful. So I'm going to discuss all three of them. What you're going to experience in my speculation is that, well, you're going to first have some propensity toward one of the perspectives, depending on your psychological makeup and like what you can do mathematically, all that stuff. And then you're going to sort of work through the other perspectives, and they are going to somewhat make sense. But then you're going to start feeling, oh, there are these three perspectives, but I cannot switch from one to the other one. It takes a while, and like, how do they connect? Okay, you're going to feel this this problem, and hopefully, by the end of this class, it's going to start making sense a little bit. So the first perspective is what I call the synthetic perspective, or the algebraic perspective, if you want. So, three perspectives. Because ultimately, the formalism of differential forms was invented to simplify many of the calculations that you've seen in vector calculus, computing curls, cross products, whatever. All of these have sort of complicated formulas, and those of you who need to use them and memorize them, of course, can do that. But often what happens is things like curl seems like it is sort of like restricted to 3 dimensions. Cross products seems like it is restricted to 3 dimensions. But for general purposes, we don't want to be subject to this restriction of 3 dimensions. Because, for instance, ultimately, perhaps, you want to do something in the special or general relativity setting. In that case, you have already 4 dimensions, and now you have to change everything, reinvent everything, stuff like that. And so differential forms somehow is sort of like a bunch of rules and a bunch of symbols that accurately generalize things like gradient, curl, divergence, things like this that you're familiar with from vector calculus. So let me write it. I really want you to develop a working understanding of differential forms. So, bunch of symbols. Subject to certain rules. Okay, that's the first step. That's the first perspective. You say, I see this. We're going to see, it's like dx whatever. We're going to have a bunch of operations. We're going to have what is called wedge product. We're going to have exterior differentiation or derivative, and something called Hodge star. Okay, these basically give you everything. Second perspective, of course, is perspective coming from differential calculus. In fact, in previous problem sets, I've been asking you guys to do certain problems that was actually developing this. And from the perspective of differential calculus, differential forms are nothing but functions taking multilinear function values. Okay. Multilinear function valued functions. Valued functions. The third is going to be the perspective coming from integral calculus. And from integral calculus, differential forms are going to be things whose signed integrals we can take over things called chains. Whose signed integrals over chains, or maybe I should have said things one can integrate, whose signed integrals over chains are defined and can be computed. Now, what is a chain? A chain is going to be something you can integrate differential forms over. Okay? We're going to see that later. Okay? And ultimately, these are going to come together within Stokes' theorem, Green's theorem, Gauss' theorem, fundamental theorem of line integrals. All of these, they're all going to be one thing. Okay? They will all look the same. Okay, so it compresses a lot, but also it makes it easier for you to remember all these things. Okay? Any comments or questions so far? No, no, they're compatible. But it takes a while to match them. Yeah. I think I want to start with 1. Okay? Just like in matrix algebra, initially you didn't learn matrices are, linear transformations, all that stuff. You started with a system of linear equations, and they told you, well, store it like this, just to make it more convenient, right? And then write this augmented matrix, do this operation, that operation, and then see, it solves the equation. They didn't tell you why. We didn't tell you. I mean, I typically don't. You get used to this idea. I think there's an H missing here, because I looked up how you write it before class. So you get used to how things operate, how things should operate, and then you start making sense out of it. And differential forms too, it's the workhorse of a lot of calculations. So although this is a class where we sort of look into the meanings of things and prove things and stuff like that, it's still a valuable thing to be able to just shut your brain down and just compute. And if you follow the rules, what you compute is going to be meaningful. You may not be aware of what the meaning is, but it's going to be meaningful. Okay? I think this is very valuable. And on the problem set that's going to be released today, there's going to be a bunch of problems in this setting as well. Okay. So I'm going to start with 1. Maybe we can do some calculations together, sample calculations. Then if you have time, I'm going to switch over to 2 a little bit. And I'm going to try to give you a sense as to how one can visualize differential forms. We have an idea as to how to visualize velocities, vectors. But differential forms, I've been telling differential forms are like momenta, or they're like speedometers. So being able to visualize differential forms are going to be important as well. And then we're going to talk about how to integrate them as well. And in fact, what's going to happen is I'm going to give you the rules for algebraic manipulation for all differential forms. And then we're going to focus on differential one forms. Okay? We're going to figure out how to think of them visually to make sense of this differential calculus perspective, how to make sense of differential one forms from differential calculus perspective, from a heuristic perspective. And then we're going to learn how to integrate them. And then we're going to sort of generalize this idea. So perspective. To keep it simpler, I'm just going to now focus on the nice case, which is the case of Rn. Okay? I'm not even considering an open set in it. Don't worry about that for now. These are going to be differential forms on Rn. So let me write it like this. Let's write it like this. This is not a formal definition. I'm going to give you a bunch of symbols. 1, dx1, dx2, ... dxn. Okay? These are atoms of your language, if you want. You don't get to split them for now. And of course, I'm thinking of a point in Rn to be x1, x2, whatever. These are all differential forms. Any linear combination of them is also a differential form. And in fact, let me say first, any scalar function multiple of them is a differential form. Okay? So where f is some function defined on Rn, taking real values. Is arbitrary, though. You get to choose any function you want. You can take a bunch of functions, multiply each one of these using these functions, add them up. Now I'm going to write that. Any linear combinations of these. But there's two more, okay? There's something called wedge product or exterior product. You get to take differential forms, two of them. You get to take their wedge product. If omega and eta are differential forms, then their wedge product, or exterior product, you could see that word as well, okay, you write it like this, and this is what you call wedge. You say omega wedge eta. Okay? This is also a differential form. We're not done. I didn't tell you how to do this yet. We'll get there. What else? One more important thing, exterior derivative, lowercase d, okay? Remember, in the context of differential calculus, we were using uppercase d, as opposed to the textbook, okay? Lowercase d is going to be what we're going to call exterior derivative. For us, that's going to be defined only for differential forms. Let me write it here. And so is its exterior derivative, d omega. We're going to write it d omega. I didn't tell you how to compute this yet, but we're going to make sense of it. Okay. And finally, there's something called Hodge star. Okay. If omega is a diff form, so is star omega, and star is called Hodge star. Okay. These are all the symbols allowed. Linear combinations work the way you would expect. Function multiplication works the way you would expect. We need to discuss how to make sense of this. That is to say, what are the rules for this? We need to make sense of the rules of d omega and also this guy. Even before I continue, I should say everything in blue applies on any open subset of any normed space. It doesn't even need to be finite dimensional. Okay, and what do I mean? Instead of looking at the differential form on Rn, I could have chosen some open subset or some norm space. These would make sense the same way. Well, perhaps the coordinates don't make sense. So maybe I should write it like this. On the other hand, this Hodge star is something special. Hodge star is defined only for oriented finite dimensional inner product spaces. If you haven't discussed what an orientation is, we're going to get there later. Ultimately, though, you should say, well, we should be interested in signed integrals. And so orientation is something related to that. And you should think of things like, oh, the right-hand rule or the left-hand rule, whatever. This we're going to discuss later. Okay. So this is the scope of these symbols, but I still haven't finished how to operate these. Rules are this. Okay. First of all, any differential form ultimately then is a linear combination of, well, let me write it explicitly. Any differential form on Rn is of the form omega equals, okay? This is a constant function 1 if you want. I get to multiply it by any function whatsoever, okay? I'm going to denote it by f sub 0, but maybe instead of n, let's look at R3, the context that you're most familiar with, is of the form omega f 0, 0, 0, f1, 0, 0, dx plus f0, 1, 0, dy plus f0, 0, 1, dz. Okay. I just took these guys, multiplied all of these by some functions. That's allowed. I can take their linear combination. That's allowed. But we're not done yet. Now you take wedges, okay? You say, for instance, 1, 1, 0, dx wedge dy plus f1, 0, 1, dx wedge dz plus f0, 1, 1, dy wedge dz plus, now you wedge one more, okay? Now you have x, y, z. So that's all there is to it. The rules for wedge and d are so that this is in fact true. Because for instance, you could say, why don't I have dx wedge dx here? Okay, I'm saying as a rule, if you wedge one of these against itself, you get 0, cancels out. In fact, more generally, the statement, the rule is this. If you wedge dxi with dxj, you get to flip the orders, but then you pick up a minus. Okay, that's the rule. The minus here. Just saying this is the rule for wedge. Okay. In particular, if you wedge dxi with itself, well, if you flip, you're going to get back the same thing. But I'm saying it's something that is equal to its negative. That means 0 for me, okay? So it cancels out. Maybe I should write it. Cancel it out. And that's why I wedge at most 3 of these standard forms. Because if I were to use one more, at least one of these, there would be one repetition. Okay? And how do I get to say that? Because of this. Maybe I should do it here because rules are not done. So for instance, okay, let's say I took this guy. Forget about the function part. Just look at this part. Let's say I wedge another dx to it. I'm saying that, in fact, this rule implies that this has to be 0. Why? Because you say, well, flip these two, pick up a minus. So minus dx wedge dy wedge dx wedge dz. You flipped these two. This should be reminiscent of sort of row reduction and how determinant operates. Okay? Now you do it one more time. Let's say it this way. So now you pick up one more minus, so now it's a plus. dx wedge dy wedge dz. Okay? Now if you were to flip these two, I'm saying it's 0. If you wedge anything by 0, it's 0. Okay? I'm just describing how things should operate. What about wedging something that has a function next to it? Well, functions you get to take out, okay? So if you were to wedge omega against f eta, you get to take f all the way there. Okay? For free. Doesn't do anything. Okay? So really, even though in the middle, when you're doing these wedge operations, you could have function multiples, you can always take them all the way to the beginning. Okay? These are the wedge rules. The D rule is this. Or there are 2 of them. Rules continued. It's another rule. So 1 itself, I said, is a differential form. That means any function, any scalar function by itself is a differential form. F is a differential form, any function. Its D is the derivative. But I'm going to write it this way. Okay. This is going to be a certain linear combination of the standard coordinate forms. And it's going to be nothing but this multiply the first, so dx1 plus second partial multiplied with the second coordinate differential all the way up to here. Okay. What if I have f times some more differential form, some other differential form? I want to be careful here. Just so that I don't need to change my notation later. Let's see. Well, I think that's enough, actually. Actually, I don't think I need to say anything any further. Well, just to be safe, let's also syntactically say it is like this. If you do d twice, you get 0. Okay. And because I want this to happen, we didn't use lowercase d as the derivative, because I don't want you to think of that as the second derivative. Okay. Now, in the case of R3, I feel like I'm forgetting one of the rules, but I'll update it on Monday. Just like in polynomials, we're going to say this is if I didn't have anything else, this would be a 0 form. Anything of this form would be a 1 form. Anything of this form would be a 2 form. And anything of this form would be a 3 form. So when you see expressions, differential forms, you look at how many dxi's are you wedging together. The number of that is going to give you the degree of the differential form. Differential 1 form, 2 form, 3 form. Okay. So this is going to be the 1 forms. These are going to be the second 2 forms. These are going to be the third 3 forms. 1 forms we're going to differentiate over 1 chains. These are 1-dimensional spaces or regions. 2 forms we're going to differentiate over 2-dimensional chains, 2 chains. 3 forms we're going to differentiate over 3 chains, and so on. Okay. I think that's a good place to stop. Thank you. I'll see you on Monday.